In this video, we will talk about gradient descent, but not just how the algorithm works. We are going to dig into the statistical why behind it. Why does this formula look the way it does? What does it actually have to do with statistics, and what is the math that makes it work? Now you have probably seen the gradient descent update rule somewhere. Theta new equals theta old minus eta times the gradient of the loss function. It looks neat. It works in practice. But where does it actually come from? Why subtract the gradient? Why is there a learning rate? And why does this single algorithm sit at the heart of almost every modern statistical model, from logistic regression to neural networks? By the end of this video, you will understand all of it from first principles. We will start with the statistical reason we even need an algorithm like this. Then we will build the intuition, the hill, the fog, the steps downward. Then we will derive the update rule using Taylor's theorem line by line. And finally, we will connect it back to the statistical estimators you already know. Least squares, maximum likelihood, all of them. No leaps, just one careful step after another. Let us begin. Let us start with something you might not have noticed. Almost every statistical estimator you have ever learned is actually the answer to an optimization problem. Take ordinary least squares. Fitting a line through scattered data, we pick the slope and intercept that minimize the sum of squared errors. That is optimization. Take maximum likelihood estimation. We pick the parameters that maximize the likelihood of observing our data. Maximizing is the same as minimizing the negative. So MLE is also optimization. Take logistic regression. We minimize the cross entropy loss. Take ridge regression. We minimize sum of squared errors plus a penalty term. Even maximum a posteriori estimation or MAP minimizes the negative loss of the posterior. Every single one of these is the same shape of problem. We have some function L of theta, call it the loss function, and we want to find the value of theta that makes L of theta as small as possible. Now here is the question. For some of these, we can solve the optimization problem with paper and pen. Ordinary least squares has a beautiful closed form answer. Beta hat equals x transpose x inverse times x transpose y. You take a derivative, set it to 0, solve, done. But for most loss functions in modern statistics, logistic regression, neural networks, mixture models, almost anything non-trivial, there is no clean algebraic solution. The derivative equals 0 equation is too messy to solve by hand. So we need an algorithm, something that can start from a guess, look at the loss function and improve the guess step by step until it lands near the minimum. That algorithm is gradient descent. And the reason we need it is purely statistical. Because the estimators we want are defined as minimizers of loss functions that we cannot solve analytically. Before we touch any math, let us build the intuition. Imagine you are standing on a hillside, it is foggy, you can see only the patch of ground directly around your feet. Your goal is to reach the bottom of the valley. How do you do it? Simple. You look around your feet, you ask yourself, which direction is steepest downhill? You take a small step in that direction. Now you are at a new position. You look around your feet again and again. Which way is steepest down? Step, repeat, repeat. Eventually, the ground around you stops sloping. You have arrived at the bottom. That is gradient descent. The hill is the loss function. Your position on the hill is the current value of the parameter theta. Your altitude is the loss L of theta. And the direction of steepest descent is given by something called the negative gradient. The gradient, written as nabla L of theta, is a vector that points in the direction of steepest ascent, the direction in which the function increases fastest. So the negative of the gradient minus nabla L of theta points in the direction of steepest descent, the way down. And that is why the gradient descent update rule has a minus sign. You're moving in the negative gradient direction. The eta, the learning rate, controls how big a step you take. A larger eta means bigger steps. A smaller eta means tinier, more cautious steps. We will come back to why that matters. So the algorithm in one line: start somewhere, compute the gradient, take a step opposite to it, repeat. That is it. Now let us see why this actually works mathematically. Because the magic is not in the metaphor, the magic is in Taylor's theorem. Now here is the question that matters. We claim that moving in the direction of minus the gradient decreases the loss. Why? What is the actual mathematical reason? The answer is Taylor's theorem. You have probably seen it before. It is the result that let us approximate any smooth function near a point using its derivatives. Let me walk through it slowly. Suppose we are at the point theta and we move by a small amount delta theta. So our new position is theta plus delta theta. What is L at the new position? Taylor's theorem says that for small delta theta we can write L of theta plus delta theta is approximately equal to L of theta plus the gradient L at theta dot product with delta theta. There is also a second order term involving the Hessian, but for now the small delta theta approximation drops it. Now here is where the algebra becomes beautiful. We want L at the new position to be less than L at the old position. We want a decrease. Looking at a Taylor expansion, that means we need the second term, the gradient dotted with delta theta, to be negative. So we need to choose delta theta such that this dot product is as negative as possible. From basic vector geometry, the dot product of two vectors is most negative when the two vectors point in exactly opposite directions. So delta theta should point in the opposite direction of the gradient. Specifically, set delta theta equal to minus eta times the gradient of L, where eta is a small positive number. Substitute this back into a Taylor expansion. We get L of theta minus eta times nabla L is approximately L of theta plus the gradient dotted with minus eta times the gradient, which simplifies to L of theta minus eta times the gradient dotted with itself, which is minus eta times the squared length of the gradient. The square of a length is always non-negative. So we are guaranteed that L decreases as long as the gradient is not 0 and as long as eta is small enough that the linear approximation is valid. That is the statistical why. That is the entire mathematical justification for gradient descent. We are not moving downhill because someone said so. We are moving downhill because Taylor's theorem tells us to first order, and that this is the steepest possible local decrease in the loss function. Now let us talk more about eta, the learning rate. We just derived that the loss decreases by eta times the squared norm of the gradient, provided eta is small. But what does small mean? And what happens if it is not? Recall, our Taylor approximation only holds for small delta theta. If we take a huge step, the linear approximation falls apart. The loss surface curves. The higher order terms we ignored come back to bite us. Let me show you what this looks like in practice. Picture our loss ball again. We start somewhere on one side. If eta is too small, we take tiny baby steps. We do move downward. Every step decreases the loss, but it takes forever. We need thousands of iterations to crawl down a simple parabola. Eta too small means slow convergence. If eta is just right, we step decisively towards the minimum. A few dozen steps and we are there. Eta just right means fast convergence. But if eta is too big, here is what happens. We overshoot the bottom of the bowl. Now we are on the other side, higher up than before. The next step overshoots back. We bounce side to side, sometimes climbing higher with each bounce, we diverge. The loss explodes. Eta too big means the algorithm breaks. The takeaway is that there is no universally correct learning rate. It depends on the shape of your loss function. For a steep, narrow bowl, you need a small eta. For a wide, shallow bowl, you can use a larger one. In practice, we tune eta by trial and error. or use clever schemes like learning rate schedules and adaptive methods such as ADAM, but that is another video. For now, just remember the trade-off. Too small, slow. Too big, broken. Just right, convergence. Let us now run gradient descent end-to-end on a real statistical problem. Simple linear regression. We have data, x and y pairs. We want to fit a line y equals beta times x passing through the origin for simplicity single parameter. Our loss function is the sum of squared errors. L of beta equals the sum over I of yi minus beta times xi all squared. Now step 1, compute the gradient. dl by d beta equals minus 2 times the sum over I of xi times the quantity yi minus beta xi. Step 2, pick a starting beta. Say beta equals 0. Pick a learning rate. Say eta equals 0.01. Step 3, apply the update. Beta new equals beta old minus eta times dl by d beta evaluated at beta old. Let us run this with three data points. X equals 1, 2, 3 and y equals 2, 4, 6. The true beta is 2. Start at beta equals 0. Iteration 1. The errors are yi minus 0 times xi, which is just yi. So we get 2, 4, 6. And multiply each by xi and sum, that is 1 times 2 plus 2 times 4 plus 3 times 6 equals 28. Multiply by minus 2 minus 56. So the gradient at beta equals 0 is minus 56. Beta nu equals 0 minus 0.01 time minus 56, which equals plus 0.56. Good. We moved in the right direction towards 2. Now iteration 2. Recompute errors at beta equals 0.56. yi minus 0.56 times xi. For x equals 1, 2 minus 0.56, 1.44. For x equals 2, 4 minus 1.12, 2.88. For x equals 3, 6 minus 1.68, 4.32. Multiply each by xi and sum. 1.44 plus 5.76 plus 12.96 equals 20.16. Multiply by minus 2 minus 40.32. Now beta equals 0.56 minus 0.01 times minus 40.32 equals 0.96. Now we are getting closer to 2. Keep iterating. After 10 iterations, beta is 1.93. After 30 iterations, it is essentially 2. We just used gradient descent to compute the least square estimator by hand from scratch. Now this particular problem has a closed form solution. Beta hat equals sum of xi yi divided by sum of xi squared, which equals 28 divided by 14 equals 2. So we did not strictly need gradient descent here. But for models without a closed form, logistic regression, deep neural networks, anything non-trivial, this iterative procedure is the only practical way. Now a question that might be nagging you. We have shown that gradient descent steps downhill. The loss decreases at each step. But does it eventually reach the global minimum? Or could it get stuck somewhere along the way? The answer depends on the shape of the loss function. If the loss function is convex, that is, shaped like a bowl with a single valley and no local dips, then gradient descent is guaranteed to reach the global minimum, given enough iterations and a small enough learning rate. Convex functions have one and only one minimum, and any direction of downhill movement leads toward it. The good news is that the most classical statistical loss functions are convex. The sum of squared errors in linear regression, convex. The negative log likelihood in logistic regression, convex. Ridge and lasso losses, convex. For all of these, gradient descent finds the true optimum. The bad news comes when we move to deep neural networks. Neural network loss functions are highly non-convex. They have many local minima, saddle points, plateaus, and ridges. There is no guarantee that gradient descent reaches the global minimum. In practice, though, it works remarkably well for reasons that are still an active area of research. So, when you use gradient descent on a classical statistical model, you can trust the answer. When you use it on a neural network, you trust empirically, not theoretically. Now, there is one more piece to this story, and it is the most statistical piece of all. When your data set is small, 3 points, 100 points, computing the gradient over of all of them is trivial. Scale that up. A million training examples, a billion. Now computing the full gradient, that sum over all I, takes minutes or hours per single step. We need thousands of steps. The whole procedure becomes infeasible. So we cheat. Instead of computing the gradient using all the data, we compute the gradient using just one randomly selected example on a small batch, say 32 examples. This gives us an estimate of the true gradient, a noisy statistical estimate. Then we take a step using that noisy estimate. Now, this is where statistics earns its name in the algorithm. By the linearity of expectation, the gradient computed on a randomly chosen example is an unbiased estimator of the true average gradient over the full data set. The expected value of the sample gradient equals the true gradient. So in expectation, we are still moving in the right direction. The individual steps are noisy. They do not point exactly downhill on each iteration, but on average, they do. And by the law of large numbers over many iterations, the noise averages out and convergence still happens. This is stochastic gradient descent, SGD. It is faster per step, scales beautifully to huge data sets, and surprisingly often works better than full batch gradient descent. The noise actually helps escape shallow local minima in non-convex landscapes. SGD is the workhorse of modern machine learning, and it is a statistical estimator all the way down. The gradient itself is being estimated from a sample. Now let us put everything together in one reference card. 6 things to remember. Simple. 1. The goal. Find theta that minimizes L of theta. This is where what every statistical estimator reduces to. 2. The update rule. Theta new equals theta old minus eta times the gradient of L at old theta. 3. The justification. From Taylor's first order expansion, L decreases by approximately eta times the squared norm of the gradient. That is the why. 4th, the learning rate. Too small means slow. Too big means divergence. Tune carefully. 5th, the convexity guarantee. Convex losses converge to a global minimum. Non-convex losses converge to some local minimum. Most classical statistical losses are convex. And 6th, stochastic gradient descent. Replace the full gradient with a sample-based unbiased estimator. Scales to huge data sets. Screenshot this card. Keep it next to your notebook. So just to recap what we covered, gradient descent is not a mysterious black box theorem. It is a direct consequence of Taylor's theorem applied to the optimization problems that define every statistical estimators we use. The hill metaphor is just an intuition for the first order approximation. The minus sign in the update rule comes from wanting the dot product with the gradient to be negative. The learning rate exists because the Taylor approximation only holds for small steps. The convexity story tells us when convergence to be global minimum is guaranteed. And stochastic gradient descent makes the whole machinery scale to massive datasets by using a sample of the gradient instead of the full thing, an unbiased statistical estimator standing in for an expensive sum. Next time you write theta new equals theta old minus eta times the gradient in any code, any model, anywhere, you will know exactly why each piece of that line is there and what makes it work. The math is not intimidating once you see it clearly. It is just arithmetic in service of a very precise question. Where is the minimum of this function?